February 23, 1943, arrival at Kummersdorf and the first inspection. Midday light was thin and iron cold over Kummersdorf proving ground. A ring of concrete tracks and test pits lay a few dozen kilometers southeast of Berlin. The wind carried the metallic tang of fuel. It carried the colder, drier bite of winter from the forests beyond. In Hangar 3, the lamps threw hard circles of light. Mechanics moved with the precise economy of men who had spent long hours coaxing life out of machines. At the center of those lamps, breast high on stout timbers, sat an American M4A1 Sherman, serial USA 306 Sendes 641, the vehicle known among Allied crews as War Daddy 2, now stamped into German records as Versuchsfahrzeug 259. It had come a long way. Pulled from North African sand, crated, shipped by convoy, unloaded here under strict orders from Oberkommando des Heeres. For those present, it was both trophy and puzzle. Major Ernst Kniepkamp stood with his hands folded behind his back. The leather of his gloves, creased with the same grease that blackened the palms of the mechanics around him. Kniepkamp was 50, thin-cheeked, with an engineer's stare. A man who had designed track suspensions. A man who had argued with ordnance departments until he had to accept compromises. He had been assigned to lead the technical evaluation. Not a propagandist, not a bureaucrat, but one of Germany's preeminent armor engineers. Called to explain why machines fought, why they failed, and why they sometimes betrayed their makers. Around him clustered a small, chosen team. Oberengineer Franz Weber, transmission specialist, Dr. Heinrich Löwe, metallurgist, Oberfeldwebel Karl Müller, a Panzer veteran who had lost a tank in North Africa, and a translator, who held in his hands the English maintenance manual that had made the journey along with the hull. The Sherman looked smaller under the lamps than the photos had suggested. Its profile was utilitarian rather than elegant. Welded plates with visible seams, a riveted or bolted turret ring. On closer inspection revealed American assembly choices that favored speed over monolithic casting. Sand and salt from Tunisia dusted the sills. Daubs of desert-caked grease circled the return rollers. Someone had stenciled a winged white star on the rear hull. Someone else had scrawled an instruction in English. Do not scrap for oak. And preserved like a message in a bottle, they began the work with routine rituals, quick photographs, inventory of serial numbers and fittings, the removal of external plates, to bring the vehicle into the bright anonymity of inspection. The first impressions were what engineers notice first. Access, organization, the logic of service points. Where Panthers and Tigers had panels that required cranes, hoists, and 20 hands. The Sherman surrendered its innards to a couple of wrenches and a practiced pull. The bilge drains came free. Filter housings were visible and accessible. The engine cowling unlatched to reveal a compact radial drive. It sat like an aircraft heart in a steel ribcage. Kniepkamp's catalog mind recorded these facts without drama. But his eyes hardened when Weber crouched at the transmission casing. He tapped the exposed teeth with a gloved knuckle. The sound was solid and flat. Weber's face, usually a ledger of professional calm, went white. He called for beam lamps, then for calipers. Mechanics gathered, silent now, as if they were listening to the tank speak. The gearbox was opened carefully. The room smelled of hot oil and cold metal. When the lamps washed across the gears, an involuntary murmur moved through the assembly. Helical-cut herringbone gears, machined to fine tolerance. Their faces showed a wear pattern that meant long service, but not abuse. The teeth met across a broad face. Axial thrust, the scourge of German final drives and preselector systems, was neutralized by simple geometry. Weber's finger traced the tooth profile like a priest tracing scripture. "This is not what we expected," Weber muttered. "It is not crude." Kniepkamp crouched, measuring the backlash on a micrometer. He barked one question at Dr. Loa. Alloy composition. Loa took a shaving with an abrasive, slipped it under the microscope. Within the hour, reported zinc and nickel levels, heat treatment signatures that spoke of consistent processes, mass production quality control. Are not perfect. Fielded machines never are, but uniform, predictable, durable. The team worked with a growing, uncomfortable enthusiasm. Panels came off in minutes that would have taken hours on German vehicles. The engine, a Continental. R975 radial adapted from aviation, was bolted in with serviceability in mind. Tracks were sectional. Individual links replaced without specialized presses. Fuel lines and filter housings showed redundancies. The layout of crew stowage and tool racks favored access and quick repair. Each discovery was a counterpoint to lessons the team had been taught since childhood. That armor equaled superiority. That heavier, thicker, and more complex meant better. Outside, the proving ground's diesel-scented wind whispered around the hangar. Inside, flashes of light from welders and torches painted faces in staccato. Kniepkamp's notebook began to fill, not just with dimensions and tooth profiles, but with comparisons, kilometers to failure, man-hours to service, and the quiet arithmetic of logistics. He had seen Panther final drives fail in the field after a few hundred kilometers. Here, the Sherman's transmission showed signs of having run reliably for thousands. He made a note to request captured maintenance logs and unit reports. If the tank had documentation, it would tell the story of its life as plainly as the scrapes along its flank. A junior mechanic, hands black to the knuckles, ran his palm along the inside of the turret ring and remarked under his breath on crew ergonomics. A Panzer driver, Müller, climbed into the driver's seat. He blinked under the glare. He had spent months cursing pre-selector clutches and heavy steering. He moved the Sherman's controls. His eyebrows rose. Visibility was better. Controls were lighter. After a few minutes, he climbed down, dusted his hands, and said, "A crew could drive this all day." Kniepkamp did not smile. The work had only begun. But already the contours of a disturbing thesis sketched themselves across his page. This was not a superior weapon in the textbook sense, but it was designed to be kept in the fight. Where German doctrine prized battlefield dominance through technological breakthrough, this tank embodied a different doctrine. Keep the machines moving, keep them serviceable, multiply them. As evening thickened outside the hangar, lights hummed louder. The men prepared to close the first phase of examination. The Sherman's hull lay open. The transmission sat in an oily cradle. A file of photographs recorded each measurement. Major Ernst Kniepkamp looked at the faces around him, technicians, soldiers, an engineer. For the first time since the vehicle had been unloaded, the room felt like a tribunal. They had brought a machine to life under lamps. Now they had to interpret what it meant. Inside the gears, teardown tests and an uncomfortable accounting. The lamps had been dimmed to prevent glare. The smell of hot oil and warm metal clung to clothing as the team broke for a short supper. When they returned, the hangar took on the hush of a laboratory. Sheets of graph paper, calipers, micrometers, and translated pages from the Sherman manual were laid out like instruments in an autopsy. Major Ernst Kniepkamp moved among them with the deliberate gait of a man assembling a diagnosis. He had ordered the most intrusive test first, a complete teardown of the transmission and final drives. If there was a secret inside the Sherman, it would be told by its gears. Oberingenieur Franz Weber led the disassembly with a surgeon's patience. The outer housing came away in sections that were bolted rather than welded. Seals, bearings, and fasteners were standardized parts that fell into neat piles. Each component was tagged, photographed, and measured. The herringbone gears sat centrally, their teeth polished to a sheen where oil had rubbed them for thousands of kilometers. Weber set his calipers and measured backlash, helix angles, and tooth height. He spoke with a low intensity that made the younger mechanics lean in. "These gears are not an improvisation," he said. "They are engineered for continuous duty. Look at the surface finish, ground not cast. Look at the bearing seats. oversized for oil film. This is from a production line that knows how to do this every day. Dr. Heinrich Loh's metallurgical analysis corroborated Weber's impression. Microscopic sections showed consistent heat treatment, uniform grain structure, an absence of the plate-like segregation that had started to appear in German armor as wartime shortages forced substitutions. Loh tapped a small chart onto the table, his finger moving along rows of hardness readings and carbon profiles. What you see here, Loh explained, is process control. That uniformity means predictable wear. You can plan maintenance cycles with confidence. Your Panther components are excellent when new, but variable in lifetime. Here, longevity is a design parameter. The team then turned to motion tests. A German test rig, crude by American standards but precise in their hands, was used to spool the transmission under simulated loads. Mechanics watched the gear mesh in dim magnified light as the shaft spun. Temperatures were monitored, vibrations recorded, stresses calculated. The herringbone pattern reduced axial thrust so effectively that the bearings carried pure radial loads. Thermal gradients were small and predictable. When a Panther transmission was put under similar simulated strain, the readings spiked. Axial loads rose. Bearings heated unevenly. Micro-movements in the gearbox housing became audible as worrying ticks. Kniepkamp closed his notebook and read aloud an entry he had not meant to say aloud. A device that levels the maintenance curve equalizes the battlefield. The room fell into a different, sharper silence. That arithmetic, machines available versus machines in repair, had been hinted at in reports from the front. But here it was rendered in torque curves and Hertzian contact maps. Next came the removal test. Weber's crew timed how long it would take to extract the Sherman's engine as an assembly. 2 engineers with standard tools worked methodically. Unbolt mounts, disconnect plumbing, lower the radial power plant out of its cradle on slings. They finished within 3 hours, when 2 German mechanics attempted the same with a Panther Maybach engine. The procedure demanded jigs, lifting gantries, and a small team over the better part of 2 days. The difference was not just in time. It was in the logistics and the exposure. A Sherman engine change could be performed at a field-forward area under threat. A Panther required a depot and relative safety. But mechanical advantages tell only part of the story. Kniepkamp had insisted on a human endurance test. He asked Oberfeldwebel Karl Müller, who had driven in desert heat and winter mud, to sit in the Sherman's driver's position and operate the controls for an extended period while engineers monitored fatigue markers. Müller drove across rough test sectors, navigated simulated obstacles, reported back. He spoke of light steering, a clutch that engaged without brute force, and a cockpit that allowed him to see the terrain. After the trial, Müller was asked to perform the same routine in a Panther mock-up. His shoulders tensed at the recollection. "You tire before the battlefield," he said. "The tank takes from the crew what it takes to move." Kniepkamp's notes now collected human data with the same rigor he had applied to metal. He recorded the time to complete repair tasks, the number of man-hours to replace critical components, and the number of specialized tools required. He compared these against captured maintenance logs and frontline reports he had requisitioned from intelligence units. Average Panther downtime, miles to failure, repair parts backlogs. The pattern hardened into a conclusion that pricked at Doctrine. Technical superiority loses meaning if a weapon cannot be kept in the fight. They tested recovery scenarios next. A towed Sherman immobilized by a damaged final drive could be brought back within hours. The final drive swapped at a repair point. Panthers with similar failures often awaited salvage that never came. The complexity of the mechanism, the sheer mass of the vehicle, and the scarcity of special parts meant abandonment. The team dug into intercepted logistical telegrams and factory output tables. The numbers were merciless. American automotive giants, converted into war machines, produced parts, transmissions, and engines in industrial volumes that German industry could not hope to match. Even if Germany's machines were on paper superior, the production rate, spare parts pipeline, and ease of maintenance gave the Sherman a multiplying factor. This was not simply national pride speaking. It was industrial mathematics. A reliable tank fielded in quantity became a force multiplier. A spectacular tank, rare and fragile, became a resource sink. Kniepkamp's equations used mundane data, man-hours per repair, lead time for parts, transport vulnerability, and turned them into projected combat-ready ratios. He modeled attrition not by enemy fire alone, but by mechanical attrition and supply chain fragility. His projections were stark. In extended operations, even with aggressive tactics, a force centered on high-maintenance heavy tanks would find itself outnumbered on the field by frontline Shermans still running. When he drafted the preliminary report to Oberkommando des Heeres, he took care with language. He described not the moral failings of doctrine, but the mechanical truths, tolerances, production variance, and maintenance calculus. He emphasized the revolutionary nature of mass-producible, maintainable design philosophy. The idea that a vehicle must be designed around being repaired quickly by average technicians under fire. He included appendices, gearbox profiles, material analyses, time and motion studies, and most importantly, a cascading series of projections demonstrating how mechanical downtime would reduce combat strength more than tactical superiority could restore it. Word traveled, slowly, up the chain. Reports were sent to WW2 6, the German armor design office. They were noted by men who had invested careers and prestige in heavy tank programs. Some took the report as a curiosity, others as insolence. Kniepkamp had not yet realized the political hazard he had created. The findings undermined a narrative the regime needed to sustain. That night, as the mechanics locked the hangar and a winter mist rolled over the proving ground, Kniepkamp sat with Weber and Loa over cups of bitter coffee. They spoke in low voices, trading technical minutiae, but beneath the conversation ran an awareness that this dismantled Sherman was more than engineering data. It was evidence of an industrial philosophy, standardization, redundancy, and mass production, that worked differently from the German model. They agreed. In a long war, the practical would likely kill the spectacular. Outside, the wind pushed snowflakes into the halo of the lamps. Inside, a list of bolt sizes and part numbers lay on the table like a litany. Major Ernst Kniepkamp closed his notebook. Tomorrow would be dedicated to field tasks, tests to simulate damage and repair under combat conditions. The conclusions being formed at Kummersdorf were technical, exacting, and potentially damning. What remained, he thought, was to see whether the Army would accept facts that contradicted faith. Field simulations, damage, recovery, and the logic of availability. Dawn arrived cold and brittle over Kummersdorf. The hangar doors were pushed open to a pale sky and a landscape stippled with frost. Major Ernst Kniepkamp ordered the Sherman rolled out onto the circular test track. This would be the day of practical demonstrations, the point at which numbers met noise, where bolts met boots, and the abstract calculus of maintenance was forced into the mud and clatter of real work. Mechanics rigged a variety of simulated combat damages: a shattered final drive casing, a sheared idler, a severed fuel line, a jammed track link. Each was chosen to replicate failures German crews had reported from the Eastern and North African fronts. The objective was not to win a duel between gun calibers, but to test whether a vehicle could be rapidly returned to service under the constraints of war. Limited tools, limited men, and the constant threat of enemy action. Oberfeldwebel Karl Müller climbed into the driver's seat with a weathered grin, a cigarette stub tucked in his sleeve. His hands were steady as he eased the Sherman around the course. The wider tracks swallowed frozen ruts without the clattering protest of heavier machines. At the first stage failure, a ruptured final drive housing, the crew halted, lifting tarpaulins, cutting away sand-colored canvas to expose the problem. Two mechanics, armed with a hand winch, portable jacks, and a field toolbox, began the repair. They worked quickly, removing the damaged carrier, swapping in a spur gear assembly from a bench stock, torquing nuts to the specified values, sealing housings with simple gaskets. The repair took under 4 hours and required no specialized hoists. A Panther with the same damage, the team later demonstrated, demanded a tractor, lifting rails, and the kind of depot support that could not be summoned under enemy pressure. Kniepkamp walked the repair pitches with the quiet attention of a surgeon watching an operation. He timed each motion, annotated requisition numbers, and noted the number of hands needed. He was less interested in the swagger of the repair than in its reproducibility. Could a typical Feldwerkstatt, ambushed on the road, perform this task? The answer, increasingly, was yes for the Sherman. and rarely for the Panther. Next, the team staged recovery operations. A disabled Sherman was to be towed by a captured German half-track with a field crew of 6. The winch cables were hooked, the tank balanced, and the convoy limped back toward the maintenance sheds. The process, measured from immobilization to depot arrival, consumed a single daylight cycle. By contrast, a disabled Panther on a similar route required artillery tractors and rail transport for even modest recovery distances. Every extra mile of distance, every hour en route, multiplied the chance that the vehicle would be abandoned to the elements, or worse, to capture by the enemy. Kniepkamp took special interest in the human cost played out in these scenarios. He watched Miller emerge from the Sherman after long periods of driving. He saw the way fatigue coiled in his shoulders, but also how the easier controls preserved his energy. He then observed a Panther crew dismount after similar stretches. Their faces were drawn, hands raw from heavy steering and clutching. Small differences in ergonomics, he understood, aggregated into strategic outcomes. A crew that could fight longer, recover faster, and repair in shallow rear areas effectively increased the pool of available combat vehicles. It was an arithmetic the High Command had not prioritized. The team also tested parts interchangeability. Sherman components, filters, pump assemblies, even certain transmission parts, were surprisingly modular across serial numbers. The American insistence on standardization meant that a field unit could operate with a stock of parts and expect a high likelihood of interchangeability. German factories producing with skilled artisans but under raw material constraints showed variance. 2 Panthers off the same line could present subtly different fittings. A component that fit one hull would sometimes need adjustment to seat in another. Standardization, Kniepkamp realized, enabled predictability, an industrial virtue that translated into battlefield resilience. By late afternoon, Kniepkamp convened a small briefing. He pulled a fresh sheet of paper from his notebook and presented comparative tables. Time to repair, man-hours required, parts interchangeability, production lead times, and projected operational readiness over a 60-day campaign. The numbers spoke bluntly. Under sustained operations, a force equipped with Shermans would maintain a significantly higher percentage of active units than one depending on high-maintenance heavy tanks. The arithmetic did not negate battlefield prowess per vehicle, but it reframed strategy. Superiority must be multiplied by presence. A messenger arrived with a terse cable from Prüf 6. 2 senior officers requested an immediate demonstration for an inspection party the following week. Kniepkamp suspected the invitation carried more than curiosity. It carried political risk. His findings undermined what had become an article of faith, that German engineering, manifested in the Panther and Tiger, would decisively dominate the armored battlefield. He also knew that industrial policy and procurement were controlled by men whose careers and reputations were bound to the heavy tank paradigm. To challenge that would be to challenge the institutional order. That evening, Kniepkamp walked the quiet line of halved vehicles and empty cranes. In the dimness, the Sherman sat like a foreign philosophy, unimposing in silhouette but potent in practice. He thought of the men in the factories in Detroit and Cleveland, assembly lines humming with interchangeable parts, thousands of hands trained to produce predictable components. Here in Germany, skilled labor was being funneled into exotic machinery, the production of which consumed time and alloy that could not be replaced. The mismatch between design elegance and industrial capacity had long worried him. The captured Sherman had not merely confirmed that worry. It had made it unavoidable. Before retiring, he drafted the outline of the upcoming demonstration. Practical tests, recovery operations, and a candid presentation of projected readiness metrics under multiple attrition scenarios. He instructed his team to prepare clear visual aids, photographs of gear teeth, charts of service times, and a concise executive summary that could not be dismissed as mere pedantry. The men left the hangar with the uneasy knowledge that data would meet doctrine, and that the outcome was politically charged. Under the stars, Kummersdorf was silent save for distant machinery and the occasional bark of a sentry. Kniepkamp sat in his small office and wrote the first lines of his report with a steady hand. He titled it simply, Operational Availability and Maintainability, Comparative Study M4A1 versus PZ KPFW-V. The title was clinical and unromantic, precisely the tone he wished to strike. He would present facts and leave judgment to his superiors. Yet as he filed photographs, calculations, and appendices into a leather folder, he could not suppress a private conviction. The war's outcome might hinge less on engineering brilliance than on the sober discipline of industrial choices. He locked the folder and, for the first time since the tank had arrived, felt the cold weight of possible consequences. The demonstration. Politics, pride, and the weight of evidence. The inspection party arrived under a low sky the following week. A procession led by a colonel from Prüf 6, with two stern-faced officers from the Heereswaffenamt and a civilian representative whose suit spoke of armaments procurement. They brought with them the atmosphere of judgment. Their polished boots clicked on the concrete as they moved through Hangar 3. Major Ernst Kniepkamp met them at the threshold, folder in hand, Grouser and Weber flanking him like quiet witnesses. Kniepkamp began with a tour, letting the inspectors see the details before he framed the thesis. He opened the gearbox once more, laid out gear teeth, and projected photographs of tooth contact patterns onto an improvised screen. He showed the maintenance log captured with the vehicle, entries that documented thousands of kilometers between major services. Then led them outside to the test track for the staged repairs and recovery demonstrations. The men watched in silence as the Sherman was immobilized, serviced, and towed back within the hours the team had promised. Metrics were read aloud, man-hours, part counts, tool lists, and predicted operational availability over sustained campaigns. At the end of the demonstration, Kniepkamp presented his conclusions in a quiet, deliberate voice. He emphasized the interchangeable parts, shorter repair times, lower logistic overhead, and industrial scalability. He argued the strategic corollary plainly. In a protracted war, machines that are available matter more than machines that are superior on paper but rarely present when needed. For a moment, there was only the sound of papers rustling. Then the senior Prüf 6 officer, a man with a well-cut uniform and a reputation for defending doctrine, leaned forward. His tone was polite but edged. "Major Kniepkamp," he said, "your engineering is admired. But on the battlefield, we have seen the Panther and Tiger inflict losses the Sherman cannot match. How do you respond to tactical reality?" Kniepkamp did not flinch. He answered with numbers, availability ratios, repair times, and the attrition model that showed cumulative combat effectiveness as a function of operational presence rather than single vehicle potency. He cited North African reports of abandoned heavy tanks, the breakdown rates, and the logistics overhead that had crippled operations more than enemy counterfire in several instances. The civilian procurement officer interjected, his voice smooth. "Our factories require time to retool. We cannot simply turn away from the technological path we have invested in. Moreover, these findings, if publicized, could be damaging to morale." It was the argument Kniepkamp had anticipated. Industrial and political inertia, prestige tied to technical brilliance, and the fear that admitting a mistake would weaken resolve. He had prepared appendices, counter-proposals showing how production emphasis could be shifted to a balance of reliable medium tanks and heavy breakthrough machines. But he knew proposals were not votes. They were recommendations to men whose careers and reputations were on the line. Still, the demonstration had been rigorous. Photos, logbooks, and mechanical readings could not be dismissed out of hand. The Prüf 6 officer nodded, guarded. "You will submit a formal report," he said. "It will be considered." Kniepkamp left the meeting with the formalities completed, but unease lodged under his sternum. His team had done everything properly. They had shown facts. The next stage, translation of facts into policy, would require more than evidence. Back at Kummersdorf, the mood among the engineers was somber. They worked through revisions to the report, tightening language and adding simulations. They included comparative production figures from captured intelligence and public sources, American mass production capacity against German artisanal output. They detailed how standard automotive manufacturing techniques, implemented by American firms retooled for war, produced spare parts, engines, and transmissions with a consistency Germany's increasingly strained industry could not match. Copies of the completed report were dispatched along the chain of command. A cover letter to the Heereswaffenamt framed the conclusions as a technical recommendation rather than a rebuke of doctrine. Still, the ink on the paper could not erase the implied indictment. German armor policy was misaligned with industrial reality. The response was slow and thin. A formal acknowledgement arrived, polite but non-committal. No orders came to adjust procurement priorities. Months passed. Panthers and Tigers continued to roll out of factories in limited numbers. Each required skilled labor, alloy steel, and complex machining time that could not be scaled quickly. Meanwhile, across the Atlantic, American production numbers rose in published reports and intelligence estimates. Thousands of M4s. Standardized parts moving through an assembly line economy. Kniepkamp watched the field reports with increasing dread. Units in the east reported heavy losses of operational tanks, not to enemy fire alone, but to broken final drives, stripped gear teeth, and seized engines. Tank parks lined roads like ruined monuments when recovery was impossible. The arithmetic of his report played out in mud and metal. In one intercepted communiqué he read, a frontline commander wrote that a battalion had been reduced not by Soviet penetration, but by mechanical attrition after a forced march. These were the same failures he had modeled on graph paper at Kummersdorf. In late 1944, the costs of policy became brutal. During the Ardennes offensive, panzer columns advanced into winter forests on vehicles that had already seen months of hard service. Fuel shortages, icy roads, and a lack of spare parts turned many of these monsters into obstructions. Accounts from recovering units described formidable machines abandoned by their crews after breakdowns, to be captured intact by advancing Allied forces. Technical reports compiled by Allied intelligence upon capture would later note the staggering condition of many German heavy tanks. Engines frozen. Final drives sheared. Tracks stretched beyond repair. Kniepkamp's report, filed quietly under protocol, became another voice among many. A sober document in a mountain of wartime bureaucracy. Its fate was less a question of accuracy than of will. The Wehrmacht hierarchy could not, or would not, rapidly alter procurement philosophies in the midst of war and ideological expectation. The Reich preferred prestige to pragmatism, yet the evidence continued to accumulate. Captured Shermans returned to Allied maintenance cycles within days or weeks. German heavy tanks often required weeks, parts from distant factories, and skilled artisans whose numbers were dwindling. Field commanders began to plan around what they had, not what they hoped for. Tactics shifted as availability problems forced improvisation. For Kniepkamp, the most bitter realization was not technical humiliation, but the human toll. He had spent his career designing machines to protect soldiers and enable victory. Now he watched as decisions informed by pride and prestige cost men hours and lives in the field. He kept working in the hope that data could still steer policy. Design recommendations for simplified drivetrains, proposals for modularity that could make German armor more maintainable. But each memo felt like a plea against a tide. Kummersdorf itself became an archive of small contradictions, a place where truth could be measured, documented, and shown. It was also a place where evidence met the immovable object of politics. The Sherman they had examined remained a quiet, practical machine waiting in a corner. An object lesson that would outlast the immediate debates. For the men who had taken it apart, it remained a source of both professional admiration and deep frustration. The data was clean. The policy was not. As winter thinned and spring hinted at thaw, Kniepkamp prepared his final technical addenda. Lessons for future design that, if implemented, might have altered the course of armored warfare. He filed them with the same meticulous care he had always shown. Whether anyone would act remained the tragic uncertainty at the heart of his work. Attrition in the field. Abandoned Panthers harvested lessons. Spring had begun, but the mud of campaigns past still clung to memories and machinery. Reports trickled into Kummersdorf with the slow, inexorable rhythm of bureaucratic dispatches. After-action notes, intercepted supply requests, and field wire transcripts that sketched a map of mechanical collapse. Major Ernst Kniepkamp read them the way a physician reads progressive lab reports, symptom by symptom until the diagnosis was undeniable. One dispatch from the Eastern Front detailed a heavy tank battalion immobilized by a cluster of final drive failures after a forced march in thawing terrain. Another from Normandy months later described Panther hulls left in fields as German units retreated under pressure. Crews had torched radios and thrown aside personal gear, but the tanks themselves stood, a testament to machinery that had survived combat but failed the logistics test. A captured Allied intelligence summary noted entire columns of Panthers and Panzer IVs abandoned with intact guns and turrets. Their crews gone because towing and depot repair were impossible under fire. Kniepkamp knew these accounts were not isolated anecdotes. They matched the projections he had run at Kummersdorf, that mechanical attrition would steadily erode frontline strength. The arithmetic was merciless. A battalion that started a campaign with 90 tanks could find itself with half by attrition alone. Breakdowns, missing spares, fuel shortages, before the first major engagement had settled. The Sherman, by contrast, kept rolling in numbers. When knocked out, many were recovered, repaired, and returned to service within days. Allied technical intelligence capitalized on this reality. Teams recovered disabled German tanks, shipped components for reverse engineering, and exploited the captured machines for propaganda and practical learning. The Allies' ability to field, repair, and replace vehicles at scale shaped operational tempo in ways that complemented battlefield tactics. Logistics was strategy. Maintenance was multiplication. Kniepkamp's inbox filled with photographs of German tanks abandoned in hedgerows. Their tracks snapped, wheels sunken into clay. He received testimony from repair crews who had been ordered to leave vehicles behind because recovery assets were tied up or destroyed by air attacks. The enemy wasn't always Soviet tanks or Allied bombers. It was the clock in the supply line. Time without parts. Time without fuel. Time without safe recovery routes. These invisible enemies reduced engineering marvels to immovable scrap. At Kummersdorf, the engineers debated remedies. Could German industry be retooled mid-war to mass-produce simpler components? Could design changes be implemented to prioritize maintainability without throwing away firepower? Kniepkamp proposed a sequence of pragmatic reforms, standardized bearings, modular final drive units, and a push for parts interchangeability across production runs. He argued for using existing automotive firms to produce redundant, simpler transmissions under license. But the proposals encountered institutional resistance. Factories were already committed. Raw materials were allocated according to pre-existing plans. The Ministry of Armaments, led by Albert Speer, balanced competing priorities under bombing raids and resource shortages. Reorienting production would have required time, raw material reallocation, and political will. The very commodities in shortest supply. The regime preferred to press forward with the prestige projects that symbolized technical superiority. Meanwhile, field commanders improvised. Some units emphasized recovery training, creating mobile workshops, and prioritizing towing assets. Others adapted tactics to minimize long marches and to avoid terrain that strained drivetrains. These local adaptations mitigated losses but could not replace the strategic advantage that robust industrial logistics gave the Allies. By late 1944, the scale of abandonment had grown grotesque. Official assessments compiled by the Panzerwaffenamt post-war recorded hundreds of heavy tanks left along retreat routes, not destroyed by enemy fire but by breakdowns, seized gearboxes and final drives that had walked themselves to ruin. Accounts from soldiers spoke of humiliation. Machines crewed and fought with pride reduced to roadside hulks. Ingenuity could not compensate for industrial imbalance. Kniepkamp lived with a compound frustration. On one hand, he felt vindicated. His technical reasoning had been validated by field outcomes. On the other, he felt impotent. His recommendations had not been adopted with the speed or scale required. The Reich's insistence on the symbolic value of heavy tanks had blinded decision-makers to the practical arithmetic that determined sustained combat power. As Allied forces pressed into Germany, captured documents revealed the depth of industrial disparity. Production figures, numbers of Shermans versus Panthers and Tigers, were stark. The United States and its allies manufactured tens of thousands of medium tanks, supported by spare parts and recovery fleets, where Germany's output of heavy tanks was limited and fragile. The very philosophy that prized the exceptional over the expendable had become a strategic handicap. When the war ended and archives were pried open, Allied analysts found Kniepkamp's Kummersdorf reports among many technical files. They were not revolutionary in the sense of containing secret weapons, but they were revelatory about doctrine. Allied historians later argued the difference in design philosophy. Reliability in mass production versus heavy specialization had decisively shaped outcomes across multiple theaters. For Kniepkamp and his colleagues, the captured Sherman at Kummersdorf remained a teaching tool and an uncomfortable reminder. It stood for a lesson that transcended shells and armor. Modern war was industrial war. Technology mattered. But the context of production, maintenance, and logistics shaped which technologies counted. The Germans had made machines of wonder. The Allies made machines that, above all, worked. Aftermath and reckoning, reports, resistance, and the unheeded warning. Winter had long since ended when the full weight of Kummersdorf's findings began to ripple past the technical bureaus and into dusty offices where policy lived and died. Major Ernst Kniepkamp's final dossier, thick with photographs, gear profiles, and time-motion studies, was catalogued, copied, and buried within the apparatus it critiqued. Official replies arrived with bureaucratic gentleness. Acknowledgments, requests for clarification, and polite denials of the report's broader strategic implications. Yet the facts could not be unmade. In the months and years that followed, they reappeared in field telegrams, unit diaries, and the grim ledger of tanks abandoned along retreat routes. Kniepkamp's immediate circle at Kummersdorf kept arguing the case in technical terms. They drafted redesign proposals that would not throw away firepower, but would simplify and standardize critical subsystems. They proposed licensed production for final drive units by civilian firms, modular engine mounts to allow faster replacement, and simplified suspension elements that could be removed and replaced in field workshops. Each proposal read like common sense to engineers, but like heresy to entrenched procurement processes. Confronting conservatism and the inertia of an industry under stress proved more difficult than confronting mechanical failure. Within German wartime bureaucracy, priorities were political as well as material. The Panther and Tiger programs had become symbols of German engineering, of supposed racial and technical superiority. To scale them back or to reassign scarce materials toward a new design philosophy would require admitting a strategic error at the highest levels. For many, that admission was unthinkable. Pride, reputations, and the propaganda value of massive armored behemoths outweighed the arithmetic of maintainability on paper. Allied intelligence, by contrast, had been quick to recognize the operational implications of mass production and standardized maintenance. Technical teams unpacked captured Shermans, cataloged spare part flows, and studied American logistical doctrines. The result was a complementary system. Not only did the Allies produce tens of thousands of medium tanks, but they built the networks, depots, recovery units, and training programs that kept those tanks in fighting shape. When they recovered a disabled tank, it was not a loss but a potential reclamation. German heavy tanks, meanwhile, were often lost permanently once their specialized components failed. Kniepkamp lived through both the immediate aftermath and the slow, painful vindication that came after the war. In captured archives, Allied historians later found his Kummersdorf report among many other technical assessments. It was referenced in post-war studies that contrasted industrial philosophies, American mass production versus German craftsmanship driven into ever more complex machines. Some critics argued that Germany's failure was inevitable, given resource constraints and Allied bombing. But Kniepkamp's work suggested a subtler truth. Choices made in design and procurement amplified those constraints. The human cost of those choices followed stories and faces. Men who had fought in frozen forests and desert heat wrote letters and testified about machines that had failed them, not because enemy shells had torn them apart, but because bearings had seized or final drives had melted away under strain. The morale of units declined when their vehicles, works of national pride, became liabilities. Commanders adapted tactics. But adaptation could not fully compensate for the simple arithmetic of vehicles present on the battlefield when shooting started. In the post-war years, military scholars and defense planners read Kummersdorf's lessons with growing interest. The captured Sherman's example entered curricula for mechanized warfare, design for maintainability, standardize parts, and build logistical systems as integral to combat doctrine. Kniepkamp's recommendations, if belatedly, found echoes in later designs and in NATO standardization programs. The revelation that the American approach to armored warfare had been to optimize the whole system rather than isolated performance metrics influenced how armies rebuilt armored forces in the Cold War. Yet the personal story of Major Ernst Kniepkamp remained bittersweet. He had been right in the particulars and prophetic in the broad strokes. His report had not been magic. It was engineering truth. But truth in wartime requires institutions willing to change. Germany's institutions were not. Kniepkamp retired from active design work, carrying with him a ledger of what might have been, a set of proposed modifications, a list of civilian manufacturers who could have produced standardized subsystems, and a painful awareness of missed opportunities. The Sherman that had started this chain of reconsideration, Versuchsfahrzeug 259, survived the war as a specimen, later inspected by Allied technical teams, photographed and studied. It went on to serve in various forms and through other nations for decades after the conflict. Its legacy was not in singular battlefield glory, but in proving a principle. Reliability at scale could trump local superiority. The machine that had seemed crude in the bright arrogance of German doctrine had, in practice, been a strategic lever. Historians looking back find in Kummersdorf the intersection of engineering, industry, and politics. Technology does not exist in a vacuum. It is forged by supply chains, factory floors, and decisions made in offices where risk, pride, and necessity clash. The captured Sherman exposed a fault line in German strategy. The belief that technical elegance alone could win wars without a supporting industrial philosophy. That belief, when tested, produced magnificent machines largely unserviceable by the demands of a protracted, industrialized war. Kniepkamp's last years were spent lecturing to young engineers, insisting on a final point. Design must begin with the user and the supply chain. A weapon is effective only if it can be made in numbers, kept in the field, and serviced by average hands under fire. He argued that the moral responsibility of an engineer is not to produce beauty on paper, but utility in practice. His words found a slow audience. Military curricula evolved. NATO allies adopted standardization practices. The Sherman's quiet lesson, less glamorous than a gun duel but more consequential, was written into manuals and taught in classrooms. When historians tally tanks by tonnage and caliber, the headline figures impress. But when they model campaigns and the attrition of readiness, the arithmetic tilts toward the design philosophy embodied by that olive-drab hull examined in a cold hangar outside Berlin in 1943. The capture of War Daddy II did not by itself change policy, but it provided evidence that one day would be read with the clarity of hindsight. Wars of the 20th century were won not by single-engine genius, but by industrial systems capable of sustaining force. Captured evidence in the long shadow? How one tank informed post-war thinking. The war ended in ruins, and the Kummersdorf files dispersed among occupying powers. Major Ernst Kniepkamp's leather folder, photographs, gear profiles, and the meticulous appendices from his 1943 report found its way into Allied hands. In cramped intelligence offices, technical officers who had weathered the conflict opened the documents and read them with a professional's mixture of curiosity and vindication. For those who had built the logistics networks that kept armored columns moving, the Kummersdorf material confirmed what they had observed on battlefields stretching from North Africa to the Rhine. Availability and sustainment determined more than single vehicle capability. Allied engineers scrutinized the herringbone gears photographed at Kummersdorf, the contour maps of heat treatment, and the time motion tables for engine swaps. They compared the notes against American production records and service manuals, and noted a crucial point. The Sherman embodied a systems approach. Its designers had not chased single-parameter excellence. They optimized the ecosystem, manufacturing, maintenance, crew ergonomics, and recovery doctrine. That realization shaped post-war doctrine and design philosophy in measurable ways. Former Wehrmacht designers like Kniepkamp entered a strange new world. Some, recruited by Allied technical missions, shared their expertise, confessing the internal debates and bureaucratic pressures that had shaped German armor programs. Kniepkamp participated in technical debriefs and meetings, offering dry principles of supply chain-driven design and cautionary notes about the limits of prestige engineering. He met Allied officers who listened politely and then, in other rooms, translated those lessons into engineering briefs that would guide NATO planning and Cold War armored doctrine. Military schools absorbed the twin lessons of Kummersdorf and the battlefield, the value of standardization and the centrality of logistics. Training emphasized that tank design was inseparable from maintenance doctrine. New manuals insisted that vehicles be built with field replacement in mind, that parts be standardized across models where possible, and that recovery and repair units be integral to operational planning rather than afterthoughts. As NATO countries rebuilt armored forces, American industrial methods and logistical doctrines proved attractive and influential. The technical specifics Kniepkamp had catalogued found echoes in post-war engineering. Herringbone gears and robust final drives were no longer curiosities but design choices to be emulated or adapted. Engine mounting schemes that allowed rapid removal became favored where operational doctrine required mobility and expeditionary operations. Modular armor and powertrain units appeared in concept drawings and prototypes. The brutal lessons of wartime abandonment had a practical offspring. Yet the story was not merely technical. Political cultures mattered. The German experience showed how elite preferences, propaganda needs, and institutional prestige can distort procurement priorities until they become liabilities. Military-industrial relationships in other nations were structured in part to avoid the extremes Germany had reached. Greater civilian industry involvement, diversified production bases, and political accountability for procurement failures. In short, Kummersdorf's single-captured Sherman acted as a case study that extended beyond gear teeth and metallurgy into how societies organize for war. Kniepkamp watched these developments with a mixed sense of relief and melancholy. Relief that the technical truth he had recorded was influencing reconstruction and doctrine. Melancholy because the suffering that validated his findings could not be undone. He continued to teach, to write, and to speak to engineers about humility before systems. In public lectures, he emphasized a phrase repeated in his notes: design for repair, design for production. He argued that the moral responsibility of engineers was to design systems that preserved lives through predictability and serviceability. Across archives and museums, WWII's lineage was traced and retold. The Sherman's later service life, post-war export modification and longevity, became part of its legacy. The tank that had caught German engineers off guard in 1943 would go on to fight, be repaired, and be used by nations with limited industrial bases precisely because its maintainability fit diverse logistical contexts. Museums displayed Shermans as artifacts of a different engineering philosophy, one that privileged the aggregate and the enduring. Historians wrote about Kummersdorf in academic journals, tracing the causal lines from captured evidence to shifts in procurement thinking. Some argued that industrial capacity alone explained outcomes. Others countered that doctrine and design choices amplified capacity into strategic advantage. Both interpretations echoed through the debates that shaped military thought during the Cold War and beyond. In classrooms, instructors used Kummersdorf as a parable. When the machinery of war is complex, the machines of administration, factories, supply chains, and training programs, become decisive weapons. Kniepkamp's final public remarks, delivered to a generation of young engineers in a modest lecture hall, were simple and precise. He recounted the day the Sherman arrived at Kummersdorf, the sound of Weber's knuckle on gears, and the slow comprehension that followed. He did not claim prophecy. He claimed observation, measurement, and the stubborn insistence that the truth of a machine is in its performance under the conditions it must survive. We chased perfection, he told the students, and forgot to ask, will it still run tomorrow? That rhetorical question found traction in institutions rethinking force structure. The captured Sherman's lesson filtered into doctrine, procurement, and design. Its influence was neither immediate nor total, but it was durable. Where German lessons had been ignored in 1943 for reasons of politics and pride, they were read carefully in the decades after. A belated appropriation of a lesson learned too late for a nation. Numbers, narratives, and the quiet victory of practical design. In the quiet aftermath, when historians and engineers tallied production and deployment figures, the arithmetic hardened into narrative. Major Ernst Kniepkamp's folders contained more than metal diagrams. They contained the seeds of a new way to measure combat power. The numbers that followed the war. Sherman production rates, Panther and Tiger outputs, maintenance logs, and operational readiness statistics confirmed what the hangar tests had suggested. Quantity and sustainment had become strategic multipliers. Kniepkamp's own appendices cited specific figures, American monthly M4 production running into the thousands, versus Germany's struggle to produce scores of Panthers and Tigers. Mean miles between failure that favored the Shermans. Depot turnaround times that further magnified the Allies' operational tempo. He had transcribed captured maintenance logs showing Shermans returning to service within days after relatively heavy damage, while German heavy tanks lingered in rail yards awaiting scarce parts. Those tables, dry and technical in their original form, were later pulled into broader studies that reshaped Cold War doctrine. Yet numbers alone do not move institutions. The Sherman's lesson had required translation into narrative. Stories commanders and factory managers could grasp. At staff colleges, instructors used Kummersdorf as a case study. A single captured tank, disassembled and measured, taught more about organizational efficacy than grand engineering ever could. The case drew a simple moral that filtered into procurement decisions, in democracies rebuilding their forces, designed for the system, not the showcase. For Kniepkamp, the moral was both professional and personal. He had lived through the exhilaration of designing novel suspension systems and the disquiet of seeing machines fail for reasons unrelated to enemy action. He had tasted the professional satisfaction of a clean technical report and the bitter flavor of institutional indifference. In later correspondence, he wrote about engineering humility, the necessity of aligning design ambitions with production realities, and the ethical duty of engineers to foresee how their creations would be sustained. The Sherman's legacy extended beyond doctrine into diplomacy and geopolitics. Post-war aid and lending programs shipped American tanks and spare parts to allies and client states, reinforcing military ties and standardizing doctrine across NATO. Those Shermans, robust and maintainable, served in diverse climates and under varied logistical conditions, proving the long-term value of a maintainable design. In theaters far from Europe, ex-Shermans fought in new wars, often operated by mechanics with minimal training because their maintenance demands were straightforward. Back at Kummersdorf, the physical remnants of the demonstration faded into archives, but the photographs and gear samples entered museum collections and technical repositories. Students and scholars visiting those archives saw not only a captured vehicle, but the fingerprint of industrial policy. The herringbone gears, the serviceable engine mounts, the stamped part numbers, each told a story about the factories, the workers, and the logistical doctrines that produced them. The story, however, retained its ironies. The Panther and Tiger, machines of genius, became icons in post-war popular imagination, impressive in museum halls and glossy photographs. The Sherman, less glamorous in individual headline moments, won in another register. Durability over drama, numbers over novelty. Public memory favored spectacle. Military professionals favored sustainment. Over time, scholarship bridged the two, and the Kummersdorf case study became required reading in professional military education. Kniepkamp died having seen some of his recommendations vindicated in post-war doctrine. Yet he remained haunted by the lost opportunities and the human cost. He continued to argue for systems thinking in engineering journals and to mentor young engineers about the perils of designing for prestige rather than for serviceability. His lectures emphasized a practical aphorism: the best design is the one that runs when it must, not merely the one that bests rival designs on a test day. The captured Sherman's most consequential lesson was procedural rather than technological. It taught that the feedback loop between frontline experience, engineering evaluation, and procurement policy must be swift and honest. If that loop becomes clogged by pride, politics, or fear, the machines of war will reflect those blockages in metal and human suffering. Kummersdorf had been a moment when the loop functioned. That is, data flowed from battlefield to lab to report. But the chain broke when policy confronted prestige. The result was a strategic mismatch whose costs were borne by soldiers and by a nation that gambled on technological mystique. In the end, the irony was stark. German armor engineers, masters of complex mechanical design, had been out-argued by American manufacturing philosophy. The captured Sherman did not possess superior armor or a more deadly gun. It possessed something less sensational and more decisive: predictability under strain and an industrial supply chain capable of keeping it in action. The victory was therefore quiet and systemic, not cinematic. As audiences watch tanks in museums or on screen, the Kummersdorf story matters because it reframes our understanding of what made a weapon effective. It was not always the biggest gun or the thickest plate, but the capacity to be produced, maintained, and returned to combat when needed. The Sherman at Kummersdorf exposed that truth under harsh light and, in doing so, offered a lesson that reshaped how militaries thought about armored warfare after 1945. Epilogue: Lessons carried forward. Years after the hangar lights had gone cold, the captured Sherman at Kummersdorf remained less an exhibit than an argument written in steel. Its presence threaded through post-war debates about procurement, doctrine, and the moral obligations of engineering. Planners who lived through 1943 now advised ministries and taught cadets. Factory foremen who had learned to press thousands of interchangeable parts into service trained new generations of machinists. The mechanic's wrenchwork, mundane and repetitive, came to be understood as decisive in ways that glamorous engineering never was. Kniepkamp's report circulated in translated form among NATO planners and defense ministries. The formulas he had sketched, relating repair time, parts pipeline, and operational availability, became formal elements of readiness modeling. Procurement officers added sustainment estimates to cost and lethality calculations. Where previously a designer could argue solely from performance curves, he now had to justify how his device would live within a supply chain. The captured tank's quiet afterlife extended into design philosophy. Cold War-era vehicles incorporated lessons, modular power packs, standardized subsystems, and doctrines that embedded recovery and depot support into operational plans. Designers spoke openly of trade-offs: armor versus maintainability, firepower versus interchangeability, and those trade-offs were now assessed against readiness curves rather than only peak performance. For historians, Kummersdorf provided a cautionary tale about institutional blindness. Technical truth can be plain, but it is not self-enforcing. The Sherman's lesson required translation into policy, and that translation depended on political will as much as engineering logic. In societies where procurement decisions were subject to public accountability and competitive industrial bases, the message found purchase more quickly than in states where prestige and propaganda distorted priorities. Major Ernst Kniepkamp died as an engineer respected for rigor and haunted by the limits of influence. He kept teaching until he could no longer stand at the blackboard, repeating the dictum that had become his professional creed: design for repair, design for production, design for the man with a wrench in the rain. His clearest legacy was not a patent or a machine, but a shift in conversation, one that acknowledged sustainment as a component of lethality. The Sherman at Kummersdorf, meanwhile, continued to serve as a concrete counterargument to myths of technological determinism. It reminded later generations that machines must be read as artifacts of systems, supply chains, factory floors, training regimens, and bureaucratic choices. When engineers and generals afterwards argued about which weapon would best secure a strategy, there was at least one stored example to consult: a practical demonstration that availability multiplies effectiveness. And so the captured tank's final lesson was modest and durable. Warfare had become industrial in a way 19th-century generals could not have foreseen. Winning required not only superior weapons, but the capacity to make, move, fix, and sustain them at scale. Kummersdorf's sheets of gear measurements and maintenance logs, once buried in a leather folder, moved slowly through archives into manuals, classrooms, and debates. In that migration, the captured Sherman achieved its truest victory. It changed, incrementally and globally, how armed forces thought about the relationship between design, industry, and human lives on the battlefield.